Hi, my name is David Beanie. I'm a retired maths teacher. I only came across the Collatz Conjecture just before I retired. So, against the advice of most mathematicians, I decided to spend a few hours working on the conjecture just to keep my mind active in retirement. Luckily, it did not take long before I found beautiful infinite patterns and formulae, which strongly suggest to me, both by common sense from the patterns and limits of the formulae, that the conjecture will be false. Having said this, my wife often tells me that I have no common sense. So I will be very interested to see if at the end of this video you agree with me that the conjecture is false. However, because infinity is such a weird and wonderful concept, something that you can never reach by counting, I am not going to make an absolute statement that the conjecture is false, even though I think it is, but I will leave it up to you to decide. I will be very happy for anyone to explain to me why there will not be any odd numbers that shoot off to infinity after seeing the patterns and limits in the video. Before I start, I want to tell you that I will not go over every step of my working, apart from the crucial bits. It would take me hours to do this. You can always check it by stopping the presentation. I also want younger viewers to be able to follow and enjoy the majority of what I am saying. So I hope you enjoy the presentation. And this is the statement of the problem if you've never seen it before. If you take any positive integer, if it is even, then divide by 2. If it is odd, then multiply by 3 and add 1. Repeat indefinitely. The Collatz conjecture states that the same end result of 1 occurs no matter which positive integer you start with. So this is a simple example. So you start off with 3, which is odd. So you multiply by 3 and add 1 to get 10, which is even. So you divide by 2 to get 5, which is odd. So you multiply by 3 and add 1 to get 16, which is even. So you divide by 2 to get 8, which is even. You divide by 2 to get 4, which is even. You divide by 2 to get 2, which is even. You divide by 2 to get 1, which is odd. So you've actually arrived at 1, as the conjecture states. Then, if you carry on from 1, because it's odd, if you multiply by 3 and add 1, you get 4. So that's even. So you divide by 2 to get 2, which is even. So you divide by 2 to get 1. And what you've got is a loop or cycle. And if you tried it again, it will go 1, 4, 2, 1, then again 1, 4, 2, 1. So it repeats itself indefinitely. Most mathematicians think that the conjecture is true. The reasons why most mathematicians think that the conjecture is true are, well, the first one is that mathematicians have tested every whole number up to 2 to the power 68, and every whole number eventually falls to 1. Second reason, any odd number is always multiplied by 3 and then 1 is added to make it an even number. It can be shown, but I'm not going to show you this, that on average, we would usually expect to divide this number by 4 to make it odd again. So when you do this, you can divide by 2, 4, 8, 16, etc. But on average, you divide by 4. Now, if you do divide by 4, this would make the original odd number smaller. So to give an example, if you start off with 9 and multiply by 3 and add 1, you get 28. And you divide by 2 to get 14 and divide by 2 to get 7. So you've gone from 9 to 7, which has made it smaller. So this is probably the main reason why most mathematicians expect all natural numbers to eventually fall to 1, because on average, over a long period, if you're dividing by 4, then they would go down. All right, I have to choose one of the following possibilities to investigate. So I thought, the first thing, maybe try to prove the conjecture. But that's a bad idea, probably, because many mathematicians of much greater ability than myself have struggled to prove the conjecture, and also it might be false. as I now think it is. So I could try to find another loop apart from the 1, 4, 2, 1 to prove that the conjecture is false. Because if there's another loop above 1, so to speak, then it wouldn't reach 1 eventually. However, it's been shown that any non-trivial cycle must have a length of at least over 17 million elements. So I do not think this would be appropriate either. But I could try to see whether any odd numbers will shoot off to infinity. Now, this seems to be the easiest possibility to investigate to me. The half of the odd numbers increase. That's 3, 7, 11, 15, etc. And I will look at just these odd numbers to see if there is any pattern in the number of consecutive increases when the Collatz procedure is followed. I will then be able to see if there are any odd numbers that will shoot off to infinity. As powers of 2 will always go straight down to 1, as we saw before, 16 went to 8, went to 4, went to 2, went to 1, are there any odd numbers that will continually increase to infinity? To this end, I have found infinite patterns and formulae for the number of consecutive increases when the Collatz formula is applied. For example, I am able to find the starting and finishing odd number and the odd numbers in between these for the Collatz procedure for any number of consecutive increases for the mth time. So if I wanted to, I could find 1,000,000 increases for the 557th time. These patterns and formulae apply to every odd number that increases, the 3, the 7, 11, etc., when the Collatz procedure is followed. But it's very important to note, though, that my definition of an increase is only when you divide by 2 once, when going from one odd number to the next odd number. E.g., if you start off with 3, because it's odd, you multiply by 3 and add 1 to get 10. And because it's even, you divide by 2 to get 5, which is the next odd number. So I've gone from 3 to 5, which is an increase. However, if you started off from 5, because it's odd, you multiply by 3 and add 1, it's increased to 16. So that's not the next odd number. So if you carried on from 16, as we saw before, it would go down to 1. So going from 5 to 1, that's a decrease, so that doesn't count. The other example, going from 9 to 7, which I've seen before, that's obviously dividing by 4, 2 twice. So that is a decrease anyway. So that's very important for the rest of the investigation. It's just going from one odd number to the next odd number, and you're always dividing by 2. Right, obviously, I will not come up with an odd number like the one shown there that will shoot off to infinity, but I will show that various limits of the formulae found will tend to infinity when the number of consecutive increases tends to infinity. It should be noted that I have discovered that the number of consecutive increases does get larger and larger and larger as the natural numbers increase, and the pattern will show this clearly. Before I do this, though, I need to mention the different sizes of infinity for natural and real numbers and power sets. The formula and patterns I have discovered will use the concepts of these different sizes of infinities and will suggest that some odd numbers will shoot off to infinity of the natural numbers and that the Collatz conjecture is false. Right, so different sizes of infinity. Mathematicians, due mainly to the work of Cantor, now mainly agree that there are different sizes of infinity. The smallest infinity is the cardinality or size of the natural numbers. This infinity is known as Aleph naught or Aleph 0, which is written, as you can see down there, as sort of N0, but it's really Aleph 0. Aleph 0 is said to be countable, and a set has cardinality Aleph0 if and only if there is a one-to-one correspondence between it and the natural numbers. So, e.g., the set of positive integers, which is really important because my investigation uses the positive integers for the number of consecutive increases, and also the set of rational numbers. Right, real numbers. The cardinality of the continuum is the size of the set of real numbers, which can be shown to be 2 to the power Aleph0. It is often denoted by C. Cantor proved that the set of real numbers is uncountably infinite, and that it was much, much greater than the cardinality of the natural numbers, and Aleph0. Thus, the following inequality is true. 2 to the power Aleph0 is greater than Aleph0, and I will be using this later. I'll also mention power sets. If A is a set, then its power set is the set of all the subsets of A. For example, if A is a set with 3 elements in it, 1, 2, 3, its power set is the subsets, which could be the empty set, the set with just 1 in it, the set with just 2 in it, 3 in it, 1 and 2, 1 and 3, 2 and 3, 1, 2 and 3. So set A has 3 elements, and its power set has 2 cubed, or 8 elements. So if set A has n elements, its power set has 2 to the power n elements. This also applies to infinite sets. The number of elements in the set of all natural numbers is Aleph0. Thus, the power set of the natural numbers has 2 to the power Aleph0 elements. And the set of real numbers also has cardinality 2 to the power Aleph0, the same as the power set of the natural numbers. And I'll be using that as well, as it says there. Right, I also need to mention, because it's very important, that during a lecture in 2021, the famous mathematician Terence Tao stated the following theorem. The gap between the powers of 2 and the powers of 3 goes to infinity. And he said this was a hindrance to proving that it was true, but it will help me prove or show that it's false. He then said this theorem had been proven, and it was a special case of Baker's theorem, which earned Alan Baker the Fields Medal. The formula I have found for the jump height, which you'll see later, involves a gap between the powers of 2 and the powers of 3, and should therefore go to infinity, which will help show my case, my thing is true. I also need to quickly mention the notation I'm going to use. So let y1 equal the starting off first odd number, y2 be the second odd number, etc. Let a1 be the number of times we divide by 2, going from the first odd number to the second odd number. Let a2 be the number of times we divide by 2 from the second odd number to the third odd number, etc. And let 2 to the power a1 be the number divided by to make the number odd again. So it's probably easier if I go over the example shown below. So if I start off with 19, which is the first odd number, and I multiply by 3 and add 1 to get 58, I divide by 2 once to get the next odd number, y2, which is 29. So that's why a1 is 1. But on the next one, going from 29 to 11, I've divided by 2 3 times. And so that's why a2 is 3. 2 to the power 3 is 8. And going from 88 to 11, I've divided it by 8. So that's where the notation is coming from. If you follow on with the example, then that will explain in more detail. But hopefully that's enough. Right, to find any patterns, I need to firstly find all the odd numbers that divide by 2, 4, 8, etc. Now I did this using the following method. I said, we'll take 3 times the first starting value, the odd number, plus 1 divided by 2 equals, and I put it equal to all the odd numbers. Then I solved this, coming up with the answer for the first odd numbers as a third, 5/3, 3, 13 over 3, 17 over 3, 7, etc. So because I knew the first starting odd numbers must be whole numbers, so then I knew the answers would be 3, 7, 11, 15, 19. The formula that generates these numbers is given by 4n minus 1. Now, this is important because it will turn up a lot later. So just to explain it, if you put in n is 1, then 4 times 1 minus 1 is 3. 4 times 2 minus 1 is 7. 4 times 3 minus 1 is 11, etc. So that's why it generates all the numbers. Right, then I did the same thing for dividing by 4 and came up with the numbers 1, 9, 17, 25, etc. and came up with a formula for that. Then repeated it for dividing by 8, 16, 32, 64, etc. and came up with this table. Right, I could have carried on, but I thought that was too boring. So what I needed to do then is find out what these numbers were mapped onto, these odd numbers. So just looking at the dividing by 2 row, so the first number is 3. So 3, if I multiply by 3 and add 1, I get 10. Then I divide by 2, I get 5. So we say that 3 is mapped onto 5. So what I did was find out what all those odd numbers were mapped onto and came up with this. Right, so I'm sure this has been found out before, but I thought it was interesting in that when you divide by 2, divide by 8, divide by 32, divide by 128, then they're all mapped onto the numbers with the formula 6n minus 1. If you divide by 4, divide by 16, 64, etc., they're all mapped onto 6n minus 5, as it says there. It should also be noted that no odd numbers are mapped onto 6n minus 3, which means that the odd numbers 3, 9, 15, 21 cannot be part of a loop. E.g., went from 3 to another number B to another number C back to 3 again, as there is no number that's mapped onto 3. Now, the diagram on the next slide shows the starting odd numbers which cannot be part of a loop. It's not part of my investigation, but I just thought it was interesting. I'll show you. Right. And as it says, it could be investigated further. Right, then, by inspection, I found out the formulae for A1 being 1, A1 being 3, 5, etc., and came up just by inspection with the formula in the black box. Then to check it out, I know that the second value of y is 3 times the first value plus 1 divided by 2 to the power of A1. So then I substituted this in and came up with 6n minus 1, which is what I wanted to come up with. I did the same, found the formula for the ones when A1 was 2, 4, 6, etc., and came up with that formula and did the same thing and showed that the second value was 6n minus 5, which is correct. What I also did, which is again not part of my investigation, I did it for 6n minus 3, but did it backwards and came up with the starting value formula. Well, you can see at the bottom, the first one was 4n minus 2 1/3, so that is impossible because you've got to get whole numbers when you substitute it in. So that's why nothing's mapped onto 6n minus 3. Right, this is where the investigation sort of starts now. So I decided I will color code the odd numbers so that it's easy for me to observe any patterns. So I will fill any odd numbers that rise, i.e. divide by 2 in blue, and any odd numbers that decrease, i.e. divide by 4, 8, 16 in pink. This is shown on the next slide, hopefully. Right, so obviously, if you're looking at the divide by 2, the top row is all blue. You can see some go to pink, some go to blue, etc. And the rest, the top row is always pink because we know that they always decrease. Right, then what I said, hopefully, I'll now indicate how many times each odd number has to be divided by 2. Might help me spot any patterns as well. And I did this using subscripts. So 3 subscript 1 means that 3, after being multiplied by 3 and 1 added, has to be divided by 2 once to get a result of 5. 29 subscript 3 means that 29, after being multiplied by 3 and 1 added, has to be divided by 2 3 times to get a result of 11. So I did that and came up with all of these values. Right, so I'm just looking at the dividing by 2 row, so to speak. Obviously, the top one, they're all subscripts of 1 because we know those are the numbers that you always divide by 2 once. Now, the ones in the 6n-1 row, I noticed very quickly there's a pattern with these. So, like the ones with subscript of 1 always have 1 pink one in between. If you look at the ones with the subscript of 2, there's always 3 numbers in between, etc. And this is the same sort of pattern when you look at the 6n-5 ones. And this pattern will appear when I do the consecutive increases. So that's why I thought I'd mention it now. Right, so I'm just doing dividing by 2, which is just the top one, as I've highlighted there. So what I did was made a bigger table just with the dividing by 2. So instead of just going up to n is 18, now goes up to n is 108. So then I can start the investigation. However, before I do this, I just want to mention one thing. Now, obviously, a pink one goes down. So what will happen is that's when the number of increases stops. So what I want you to sort of look at is, now the 5 is pink, but if you look at the 4n-1 row, the 5 appears between 3 and 7. So that's sort of 1.5 for n, if it was in the 4n-1 row. And if you do 4 times 1.5 minus 1, you do get 5. The 17 is between the 15 and 19 blue. So that would be 4.5. If you do 4 times 4.5 minus 1, you do get 17. So this comes up when I'm doing the investigation. So I just wanted to mention it. Because the pink ones are important because that's when the number of consecutive increases stops. Right, so now really is the start of the investigation. So what I've done there is highlight the first 3 times that there's 1 increase. So the black box, then obviously 3 increases to 5, but because 5 is pink, it stops. There's only 1 increase. 11 goes to 17 in the red box, 19 goes to 29 in the green box. So then I've put in yellow, as you can see below, all the ones that have 1 consecutive increase. And obviously those are the ones with the pink on the bottom. Right, so what I noticed from this is the odd numbers that have a single increase occur at n is 1, 3, 5, 7, 9, etc. And these odd numbers have a single space between them. Right, then I went on to 2 consecutive increases, which I've shown in the boxes there. So the first one with 2 consecutive increases in the black box. So just to clarify this, 7 goes to 11, which is the first increase. Then in the second black box, 11 goes to 17. Then the red one, 23 goes to 35. Then 35 goes to 53, which is 2 increases. Then the green one is 39 goes to 59, and 59 goes to 89, which is pink, so it stops. What I also want you to notice, which makes sense really, you look at the black boxes again, at the bottom of the black box, and I've highlighted all the 2s, obviously in yellow again, but the first black box has a 2 at the bottom, and the second black box has a 1. It's the same with the red boxes. I say this makes sense, really, because obviously I'm starting off with 2 increases, then I'd have 1 increase left after that. So it makes sense. So what I noticed from this, these odd numbers are 2 consecutive increases, and they occur at n's 2, 6, 10, 14, which is really 2 times 1, 2 times 3, 2 times 5, 2 times 7. Right, so I came up with the formula, n is 2 to the power 1, because we've always got 2 in front, times by 2m minus 1, and the 2m minus 1 generates the 1, 3, 5, 7, if you put m is 1, 2, 3 into those. So that's the overall formula for 2 consecutive increases. And notice we get 2 to the power 1 for 2 increases, it's 1 less. Right, I also noticed that these numbers have 3 spaces between them, but more importantly, on the second increase, the n value is multiplied by 3/2, or 1.5, to get the next n value. So if you look at the red box, then we started off with n is 6, and that goes to n is 9, so that's multiplying by 1.5, or 3/2. And the same with the green, that goes from 10 to 15. And that's the same for the black one as well. Right, and that is really important. Right, then I looked at 3 consecutive increases. So I've highlighted the first 2 of those. So in the black box, start off with 15 goes to 23, 23 goes to 35, and 35 goes to 53. Then the red ones, 47 goes to 71, and 71 goes to 107, and 107 goes to 161, which is pink again, so it stops. And same with these boxes. The black ones, the bottom, the first ones are 3 increases, then 2, then 1. And obviously I've highlighted all the 3s in yellow again, same as before for the others. So what I found this time, the odd numbers that have 3 consecutive increases occur at n is 4, 12, 20, 28, which is 4 times 1, 4 times 3, 4 times 5, 4 times 7. But the overall formula is 2 squared times 2m minus 1. 2 squared is 4. Now, obviously, straight away, I thought the last one was 2 to the power 1 times 2m minus 1. So is there some sort of pattern here? Yes, there is. I also noticed that there's 7 spaces between them. And again, you multiply by 3/2, going from one n value to the next n value. You see in the black boxes again, I started off with 4, and if you multiply that by 3/2, you get 6. If you multiply 6 by 3/2, you get 9. And the same with the red boxes, that works. Right, so on the next slide, because it's really important, I will try and explain why the n values are multiplied by 3/2, because obviously this occurs all of the time, so it's really important. Right, so if you look at the black box again, then please note that I've gone from 4 to 6. I've decided to call this first n value n1 and the second n value n2. Notice though that in the 4 box, so to speak, the bottom value 23, 6 times 4 minus 1 is 23. So that's in the 6n minus 1 row. If you go to the 6, we get 23 again, but obviously 4 times 6 minus 1 is 23. So that's why the 23s are the same there. And that will always be the case when it's increasing. Right, so what I said, if you look at the thing on the left now, the reason why you multiply by 3/2, let n equals n1, then y1 is always, as we know, 4n minus 1 or 4n1 minus 1. So we know to get y2 in this case, I multiply that by 3 and add 1 by just divide by 2, because I know it's an increasing one. When I simplify that, I get 6n1 minus 1, which makes sense, because we usually get 6n minus 1 as the mapping. Then because the 23s are the same, the 6n1 minus 1 must equal the 4n2 minus 1. So the 6n1 will equal 4n2, and simplifying that, I got n2 equals, as you can see, 3 over 2 times n1. So that's saying the first n value has got to be multiplied by 3 over 2 to get the second n value. So that's the reason why this is the case. You always see it. Right, then to make sure this was true, I then went on to the next one, 4 increases. So I just highlighted one this time. So the first 4 increase goes from 31 to 47, 47 to 71, 71 to 107, and 107 to the pink 161. So it stops. We've gone down 4, 3, 2, 1 at the bottom of the boxes again, which again makes sense. So what I noticed this time, as you can see, and I won't bore you to death, it's exactly the same sort of things. But this time, instead of being 2 squared times 2n minus 1, it's 2 cubed times 2n minus 1. So I'm guessing the next one is going to be 2 to the power 4 times 2n minus 1. But you never know. We'll see. And you do multiply by 3 over 2, going from 8 to 12 to 18 to 27, as we've seen before. Right, I also want to mention, now if you look from the starting n values, that is the first 4 increases that occurs. That's the second 3 that occurs. That is the fifth 2 that occurs, if you count them from the start. And that is the 14th 1 that occurs. Now, I'll try and explain to you why this is the case on the next slide. Right, so we know we're multiplying by 3 over 2 all of the time. So we start off with 8, and it goes to 12, etc. But I've rewritten 8 as 2 cubed times by 3 to the power 0. 3 to the power 0 is 1. I've written 12 as 2 squared times 3 to the power 1, 18 as 2 to the power 1 times 3 squared, etc. Right, now the reason, obviously, if I'm timesing by 3 over 2, then if I'm going from the first one to the second one, if I'm timesing by 3 over 2, I'm dividing by 2. That's the reason why the 2 cubed has gone to a 2 squared, because I'm dividing by 2, gone one smaller. But the 3's are increasing because I'm timesing it by 3. Right, but it's the first 4, because remember on 4 increases, we've always got a 2 cubed times by 2n minus 1. I remember 3 to the power 0 is 1. Now it's the first 4 because if you put 1 into 2n minus 1, 2 times 1 minus 1 is 1. So that's why it's the first 4. Now the next one, because we've got a 2 squared there, that means it's 3 increases. And because we've got a 3 there, 3 to the power 1, 2 times 2 minus 1 is 3. So that's why it's the second 3. It's the fifth 2 increases because we've got a 2 to the power 1, which is 1 less than 2. And the fifth, if you do 2 times 5 minus 1, you get 9, and 3 squared is 9. It's the 14th 1, because a 1, we've got a 2 to the power 0, which is 1 less. And if you do 14 times 2 minus 1, you get 27, which is 3 cubed. So that's why you're getting those values. And this first being a 4, first 4, second 3, fifth 2, etc., will continue for the rest of the NCIs as well, when you're looking at the first one that occurs. Right, so 4 consecutive increases, we multiply by 3 over 2 4 times. So that is important as well. I don't know whether I mentioned that on the last 3 increases, but it is really important. And just notice the last one, the n value is 40.5 for the pink one, which I sort of mentioned previously as well. That's why 40.5 is coming in. Right, and it says powers of 2 are decreasing by 1 as powers of 3 are increasing by 1, as I mentioned before, or try to. Right, I've also tried to highlight this in another diagram which might show it a little bit more clearly, hopefully, might not, but so I've put in when all the 1 increases are, then all the 2 increases, 3 increases are, etc. Now, the first 4, is obviously the first 4 that occurs. That is the second 3 that occurs. That is the 5th 2 that occurs. And that is the 14th 1 if we count them along. Now, if you look at the 5 above in yellow, then that is the first 5, but that goes on to the second 4 that occurs. That goes on to the 5th 3 that occurs. And then that will go on to the 14th 2. So it's, as I said before, it's the same sort of pattern occurring. This pattern will carry on forever with the values of NCI increasing in perpetuity. Very nice name, but it go on forever and ever and ever. So if we came to 1,000 increase, that will be the first 1,000 increase, but that will go on to the second 999 increase, etc. Right, I've also tried to highlight this further just to make absolutely sure because it is important. So I picked another value of n, so I picked 120 and times that by 3/2 to get 180. Then I've written both. I've written 120 as 2 cubed times 15, which is then 2 cubed times 8 minus 1. So I solve in the 2m minus 1 notation. I've done the same for 180 and got 2 squared times by 2 times 23 minus 1. Right, because it's written like this, so remember, if it's 2 cubed, that means it's 4 increases. It's always 1 less is the power. And 2 times 8 minus 1 means that it's the 8th time that this happens. So that's why it's the 8th 4. Now, this is the 23rd 3 because we've got 2 squared, which is 1 less again. So what I did then, just to check, is extend the table, this time up to 198, and highlighted 120 and 180, and it was a 4 and a 3. This was the 8th 4, and it was the 23rd 3. I counted them, obviously, from the start. Now, you might say, well, how do we know that? Well, believe me, please, but if you don't, you could take a screenshot of this and a screenshot of the previous one and count them yourself, and hopefully get the same thing. You will. Right, so then, not surprisingly, I went on to 5 increases and found this was the same sort of idea. I went from 5 to 4 to 3 to 2 to 1, last one being a pink one, and found out, yes, so that's saying that, and found out same sort of thing as before. You times it by 3/2, and as I said before, the formula has gone to 2 to the power 4 times 2m minus 1. So I'm highly likely thinking it's going to be 2 to the 5, 2m minus 1 for 6 increases. And it's the same sort of thing. I'll just let you look at this. This is the first 5 increase, second 4, 5th 3, 14th 1, and it's the 41st 1. Now, if you do 2 times 41 minus 1, you get 81, and that's, we've got 3 to the power 4, which is 81. So that's why that is the case. But we're doing the same sort of thing as before. It's following the same pattern. And we're multiplying by 3/2 5 times for 5 consecutive increases, which I've been mentioning again. And the pink one is 121.5. Right, and powers of 2 and decreasing as powers of 1 are increasing again. Right, now I've done this table. Now remember the numbers, the first 1, 2, 5, 14, 41, etc. Now you can generate those numbers from that formula I've put on the left-hand yellow box. So if you put 2m minus 1 equals 3 to the power x, then substitute values of x in, that x is 0, x is 1, 2, etc. as you can see in the table, and rearrange that to get m. You can work out the m values, which will tell you it's the sort of second time, fifth time, 14th time, etc. So I've just done the first few. This box really applies for the NCI is 9, but I won't do that. But I've just shown you where those numbers come from. And this table will carry on forever if you wanted it to. Right, this is important, so I will slow down. Thus, if I wanted to get 5 consecutive increases for the first time, I would follow these 5 steps. And obviously, these 4 steps, sorry. And obviously, you could do this for any number of consecutive increases, so that's why it's really important. So the first step is always you calculate the starting n value, which is always 2 to the power of, in this case, 5 minus 1. So it's the number of increases minus 1, which I've mentioned before, which would be 2 to the 4 in this case. The second step is then you calculate the starting odd number, y1, which would be, I substitute that into 4n minus 1 because I know that's the formula to use. And in this case, I get 63. Right, the third step, now remember, to get from the first value of n to the last value of n, I multiply by 3 over 2 5 times. So I'd multiply the n value, the starting n value, by 3 over 2 to the power of 5, which is the same as multiplying by 3 over 2 5 times, so to speak. And that would obtain the last n value, which I've simplified there to 3 to the power 5 over 2. Then I can now calculate the finishing odd number, because I know the n value, by substituting that into 4n minus 1 again. Now, this would work for 5 consecutive increases, 1,000 consecutive increases, a very, very, very large number of consecutive increases. So you get the starting odd number and the finishing odd number for that particular number of consecutive increases. Then it's easy to work out the numbers in between because you're always multiplying by 3, adding 1 and dividing by 2. Right, note also, if I wanted the 10th time that there were 5 consecutive increases, I would use the same 4 steps, but start by multiplying the n value by 2m minus 1, with m is 10 in it. So I've shown there that the first n value this time would be 304. And if you follow the same steps in 2, 3, and 4, you come up with that set of numbers for the 5 consecutive increases for the 10th time. Right, thus, if I wanted to find the 55th time that there were 2,067 consecutive increases, I would follow, as I said before, those 4 steps in the same way. So I've only put the first 2 steps just to totally clarify it. So I'd work out the first n value, which will be 2 to the power 2,067 minus 1. Then, because I want the 55th time this happened, I times that by 2 times 55 minus 1, come up with the n value, then substitute that for the second step into 4n minus 1, come up with the starting y value, then finish off steps 3 and 4. And you come up with the starting and finishing odd numbers for that particular thing. So straight away, I'm thinking, well, I could, for step 1, pick n is 2 to the any forever increasing extremely large value of the NCI minus 1. So the NCI could be not a very big number, but 1 million, 1 trillion, anything. For the starting n value. Then obviously I could multiply that by 2m minus 1 and pick a massive value for m for that. So I'm definitely thinking, yeah, this is going to go to infinity. Right, so now I can predict the first odd number that will have 6 consecutive increases. because I just want to totally be happy that I'm right in all I'm finding. And that would occur at n is 2 to the power 5, because there's one less, remember, which is 32. And if I do 4 times 32 minus 1, I get 127. So that will be the starting odd number. And when I did that, I was right. And it went down from 6 to 5 to 4 to 3, etc., the same as before. And I found that the formula was 2 to the power 5 times 2n minus 1 instead of the previous one, 2 to the power 4. And all the other things I'm telling you in my theory too, that applied as well. So yeah, good. So, and the same things happened with this. So then, just to check, I'm going to do it 2 more times very quickly. So to get 7 consecutive increases, that would start at n is 2 to the power 6, which is 64. And it did work out as that. And that went 7, 6, 5, 4, 3, 2, 1 again. And you got 2 to the power 6 times 2n minus 1, and the same things as before. Right, then one more time. I'd expect that to happen for 8 consecutive increases. It starts at n is 2 to the power 7, 128, and lo and behold, that happened. So obviously, if you extended this table on and on and on and on, then if I wanted 1,000 increase, the first one would occur at n is 2 to the power 999. Then you'd see at the bottom of the box 1,000, then the next box will be 999, etc., going right down to 1, exactly the same sort of thing as before. So this pattern will go on forever. So observations so far, very quickly. So I found that the first time that there was 1 increase, that occurred when n was 1 or 2 to the power 0. The first time there was 2 increases occurred at n is 2 to the power 1, which is 2. 3 increases occurred for the first time at 2 squared for n. 2 cubed for 4 increases, etc. Right, so the first NCI equals 8 would occur at n is 2 to the power 7, 128, which we found out before. And this pattern will carry on forever with the values of NCI increasing in perpetuity. The pattern strongly suggests to me that there will be very large starting odd numbers that will shoot off to infinity as the value of NCR is forever increasing, as the value of the odd numbers are increasing. And also, which is very important, the difference between the starting odd number and the final odd number will also never stop increasing as the values of NCI get larger. And that's simply because as the NCIs are getting larger, obviously you're doing more increases. So you're going to get a bigger difference between the starting one and the final one. And as you saw in the previous one of the previous diagrams, when you times in bigger numbers by 3/2, they're going to increase even by a larger value, so to speak. Right, so I've written down the overall formula for n. That's going to be 2 to the power of the number of consecutive increases minus 1 times by 2m minus 1. This formula covers every whole number value for n, as I said before. So all of the table will be filled in eventually if you get them going. Right. Also, remember that mathematicians have tested every whole number up to 2 to the power 68. Well, this would be under 70 consecutive increases on this diagram, extended diagram, which is not very far, really, if you think about it, as the diagram would carry on forever. So they've gone up to less than 70 increases, but obviously you could go on to millions and millions and millions and millions of increases, so to speak. Right, thus I am now in a position to be able to predict when we would have any number of consecutive increases. Now, I've Then another example, the first time there were 23 consecutive increases would occur at n equals 2 to the power 23 minus 1, and the starting odd number would be 167777215. Now, I did 23 consecutive increases because I used Excel to get the numbers on the consecutive increases. And I'm probably not very good at using Excel, but what I found is the numbers got very big very quickly. And if I was going over sort of 30 or something, then it wouldn't show all of the numbers. It's starting to give approximations to the numbers, which just doesn't help me check. So that's why I've shown an example of 23 consecutive increases. Now, I'm positive that if somebody knows a way of using Excel in a way better than me, or they've got something that can do where the answers give more values for the numbers, and tried something bigger than 23, then you get the right answer for this. So I used Excel and checked it, and it was correct. And the number after that, because you're dividing, it's a pink one, the last one, because you're dividing by either 4 or 8 or 16, etc., that will get smaller. Right, so as I said before, I came up with the overall formula for n just by looking at all of those things. And again, I'll mention again, please note that the values of the number of consecutive increases are positive integers like 1, 2, 3, 4, and they have a cardinality or a size of Aleph0 for the set of positive integers, which I'll use later. Right, so I'm now able to find the formula for the starting odd number and the finishing odd number for any number of consecutive increases for the nth time, which I said I could do at the start. Right, so I'll go over this reasonably quickly. So I've already found the formula for n, came up with that. So remember, step 2 was finding the starting odd number, and I substituted that into 4n minus 1. So when I did that and simplified it, I basically got the answer in the black box, which you can check. Then what I thought I'd do is I stick some numbers into this for the starting odd number. So I try m is 3 and the NCI value equaling 10, and came up with the starting odd number of 10239. Right, then remember, if we had 5 consecutive increases, we multiplied the starting value of n by 3/2 5 times to get the finishing n value. Thus, if we have NCI consecutive increases, we need to multiply the starting value of n by 3/2 NCI times. So that's why I've multiplied the n value by 3/2 to the power NCI. Then once I've done that, I can simplify the n value for step 3. Then step 4, remember, was finding the finishing odd number. So then I just substitute that back into 4n minus 1. Then I did that and came up with the answer in the black box, which you can check. Then I did the same thing. I substituted m equals 3 and NCI equals 10 into this to come up with the number of 590489. And remember, that's the finishing odd number. Then I used Excel to check, and lo and behold, I was correct. Brilliant. Everything's going well. Right, now on the next slides, because mathematicians, I've done this by common sense, even though my wife thinks I haven't got any, to get these formulae. Now, mathematicians might want another way of doing it, so I thought I'd better do this. Now, I'm going to explain this very quickly, and you can check this yourself. So what I did was, using the notation, I came up with the formula for the second y value, and the third y value, and the fourth y value, and the fifth y value. As you can see down there, you can check that yourself. Then I came up with the formula for the nth y value, by looking at the pattern. Now, knowing this, I can then come up with a formula for the y, or the n plus 1th y value, which I did. Now I can check this is true then, because I know that the n plus 1th y value will be 3 times the nth y value plus 1 divided by the 2 to the power an. So then I substituted this in, checked it, and the formula was correct. So I thought, yeah, good, I've got the formula correct. And I've seen this sort of thing from other people anyway. Right, then using this formula, I knew the formula for the starting odd number. And I knew that because we were dividing by 2 all of the time, 2 once, all the a values were all 1. So I substituted these things into the formula. And then what I noticed in the blue box, this was what we call a geometric progression. Now, if you don't know what a geometric progression is, I'm sorry, but if you do, great. So I used the formula for the sum of a geometric progression and then substituted this in after simplifying it. And then after all the simplification, basically I came up with the same formula as before. So it's sort of showing that my formulae are correct, hopefully. Right. So now I can come up with some reasons why I think the Collatz conjecture may be false. Now, reason 1, which I mentioned before, the jump height, and the jump height is the gap between the starting odd number and the finishing odd number, that will tend to infinity. So as the number of consecutive increases gets bigger and bigger and bigger, then the difference between the starting odd number and the finishing odd number will get larger and larger and larger. Right, so now because I know the formula for the finishing odd number and the starting odd number, I can work out the jump height, which is the difference between those. So I did that, and first of all came up with box A. Right, then I know that this can be written just in terms of powers of 2. So using logarithms, and if you don't know about logarithms, I'm sorry, I simplified all of this and went to box B and came up with the formula there. Right, now what I also want to mention, remember Terence Tao, and he said that the gap between the powers of 2 and the powers of 3 went to infinity. Well, formula A has got a gap between the powers of 2 and the powers of 3. So that should go to infinity because of Baker's theorem. Right, so, but I'm going to show it from box B. I've rewritten that. Right, but before I did this, I wanted to draw a few graphs just to clarify what was happening. So what I did was use, first of all, the NCI values ranging from 1 to 30, and just used m is 1 in the formulae, and came up with these numbers. So obviously, if I do the first term with NCI equals 1 is 3, then 5, the jump height is 2. Second one, 7 to 17, the difference is 10, etc. Right, and I notice how quickly they're increasing. Right, I highlighted the last one. So the first term in this sequence is 2, 1, 4, 7, etc. The last term is 4, 11, 7, 8, 2, etc. The jump height is 4, 11, 7, 80, etc. What I want you to notice is there's similar, they're not the same, obviously, but the jump height and the last term in the sequence are reasonably similar, and they're much, much bigger than the first term in the sequence. So that's sort of getting irrelevant, so to speak, towards apart from the other two numbers. Right, so then I drew a graph of these, and that looks very much like an exponential type of graph. And it looks like it's increasing quite significantly. Right, then I decided to do this with NCIs increasing to 600 to see what would happen. Now, when I did this, as I say, using Excel, it wouldn't give the full values. I wouldn't write all those numbers down anyway. So the numbers in there's approximations, really. Hopefully, they're reasonable approximations. And notice the last black box again. The last term and the jump height are actually looks like the same number there, but they're not the same number really because Excel's approximated them because they're both times by 2 to the power 286, which is a very big number. Then what I decided to mention is if you do something like sixth form mathematics, you might be familiar with the graphs of 2 to the power x, 3 to the power x, 10 to the power x, etc. And you might also know those two things there. The limit as x goes to infinity or tends to infinity of a to the power x is infinity for any a is greater than 1. So obviously 2 is greater than 1 and 3 is greater than 1. That's why those graphs are getting steep very quickly. They're going up and up and up very quickly and tending to infinity. Right, but notice that 3 to the power x is, it will be, if you carry it on, much, much steeper than 2 to the power of x. Right, so I'll read this out because this explains, hopefully, what I was trying to say with the black boxes in the previous slide. As the value of NCI approaches infinity, the exponential term 3 to the power NCI in the last term in the sequence grows much faster than the term 2 to the power NCI in the first term in the sequence. This is because the base 3 is larger than the base 2. Therefore, as the NCI becomes larger and larger, the contribution of 2 to the power NCI becomes negligible, can't even say it, compared to 3 to the power NCI. In other words, the term 2 to the power NCI becomes relatively insignificant in comparison to the term 3 to the power NCI. As a result, the limit of 3 to the power NCI minus 2 to the power NCI as NCI approaches infinity is effectively the same as the limit of 3 to the power NCI. In other words, as NCI approaches infinity, the expression 3 to the power NCI minus 2 to the power NCI grows without bound and approaches positive infinity. And the graph on the next slide confirms that this is likely to be the case. Now, obviously the bottom looks like it's a straight line, but it's due to the scale of the thing. It's not a straight line really, as you've seen previously, but it looks like it is because of the scale. But as you can see, the last few values are increasing much, much more than the previous ones. Right, so what I'm going to try and do now is show. So remember I said I was going to try and show this from box B. Well, what I've done is simplify this as well, come up with the second box, so to speak. And remember I mentioned that the limit as x goes to infinity of a to the power of x is infinity. Well, 2, as I said before, is greater than 1. So that should go to infinity as the NCI increases to infinity. 1.5 is greater than 1. So that should tend to infinity. I know we've got a minus 1 there, but that's going to be irrelevant compared to the very, very big number that 1.5 to the NCI is going to give. Also, we could make this 2m minus 1 as large as we want. We could make the m value massive, a massive value. So as far as I'm concerned, this is sort of showing that the jump height will go to infinity as the NCEI tends to infinity, and the NCEI will tend to infinity because the patterns will show that it gets bigger and bigger and bigger. Also, I stated earlier, I'll mention it one more time, during the lecture, Terence Tao mentioned that the gap between the powers of 2 and the powers of 3 will go to infinity, and this has been proven. So this is the gap between the powers of 2 and the powers of 3. So that should go to infinity, and the 2n minus 1 will go to infinity if you make n a massive number going to infinity. So that's the jump height will go to infinity as the NCI tends to infinity. So the Collatz conjecture may be false. I'll leave you to decide. Right, reason 2. Now I'm going to go through this very quickly because it's on very similar lines to reason 1. Obviously, in reason 1, I did the difference between the starting odd number and the finishing odd number. Reason 2, I'm going to do the ratio of the finishing odd number to the starting odd number. I'm going to do this really quickly. Right, so what I said, I worked first of all an example just to explain what it meant. So I picked m is 1 and NCI equals 30 and worked out the starting odd number and worked out the finishing odd number. And the ratio I got as 191,751 and a little bit. Right, so what this actually means is that the final odd number is 191,751 times larger than the starting odd number. So what I did then was make a table of these ratios, as you can see there, up to 30 again to start off with. Then drew a graph, which again looks like an exponential graph. Did it up to 600 again. And got this graph, which shows this again rising much more quickly when it gets to sort of 600. Then I found the limit of these because I had the formula for the limits, the finishing odd number and the starting odd number. I could then write down the formula for the ratio, which is the one in the black box, as you can see. Right, then I worked out the limit of the ratio of this. But I don't want to go through this really because it'll take too long. I don't want to bore you to death. Now, I'll just quickly mention the yellow box at the bottom. Now, if you've done, as I said, sixth form maths, you might be familiar with these things. So we have got that in there in my simplification. Now, the second part, the 1 over 2 times 2 to the power NCI, as the NCI approaches infinity, that'll be 1 over a very, very big number, which would approach 0. So basically, that limit of that thing would go to infinity, because the first term goes to infinity, and the second term goes to 0. Now, I did that again with the 2m minus 1 involved on the right, and I got the same answer. I also did it using probably my usual method, where you divide every term by 3 to the power NCI, then do the limit of that. I got the same sort of answer, infinity again. Right, then very, very quickly this time, I did the ratio of the jump height to the starting odd number and got values for those, a graph for that, did it again for 600, another graph, and did the ratio of those, used those things in the yellow box again, and came up with infinity again. Right, reason 4, I'll go definitely slower because now I've never taught this before. I've just read it in a book, a very nice book. But but it makes sense to me. So I thought, well, let's go for it and see what you think. Right, so I'm going to use these different sizes of infinity. Now, I'll just sort of mention before, remember the size of the positive integers and the natural numbers was Aleph0, but a much, much bigger infinity is the size of the real numbers and power set, which is 2 to the power Aleph0. And that's what I'm going to use in this. Right, so I'll try. Right, so what I first of all wrote down was a starting number of consecutive increases, 1, 2, 3, 4, 5, 6. And then I worked out 2 to the power NCI, came up with all those answers. Obviously, 2 to the power 6 is 64. Then I worked out, because I knew the formula, the first starting odd number. I knew the formula for that. And the first finishing odd number, I knew the formula for those, so I worked out those. What I want you to look at, just look at, say, the number of consecutive increases being 3. So obviously 2 to the power 3 is 8. That's where the 2 to the power NCI is coming from. Then the first starting odd number, that's 2 times 2 to the power 3 minus 1, which I got 15. Notice that is larger than 8. The first finishing odd number, not surprisingly, 2 times 3 to the NCI minus 1, I got 53. That's larger than the starting odd number, which makes sense, and it's larger than the 8 as well. And the same with the other sort of things. The numbers get bigger as you go to the right, so to speak. Right, then I said, the NCIs contain values 1, 2, 3, 4, which are positive integers. The cardinality of the set of positive integers is Aleph0. So then I filled in the final value, which is Aleph0. So then the next one is 2 to the power Aleph0, which sounds familiar. Remember, that is the infinity of the real numbers or power set of the natural numbers. So Cantor proved that 2 to the power Aleph0 is greater than Aleph0, which we can see sort of in the boxes anyway. Right, then what I said, not surprisingly, is that this next thing would be that, and that definitely should be also greater than Aleph0, because it's greater than or equivalent to at least the infinity of the real numbers. And the final thing was also greater than Aleph0, which is greater than the infinity of the positive integers. Right, I'll read the thing that's in there. I thus need to find the value of NCI, which I will denote by the letter A, which has a finishing value of Aleph0, the infinity of the positive integers, as this is the cardinality of the positive integers. Because I know the 2 times 3 to the power Aleph0 minus 1 isn't really possible for the positive integers, then I've got to find the finishing value when it's Aleph0, and I've called the number of consecutive increases A. So I fill that in there, so then I can fill in the next 2 boxes as well. Right, now what I said, which made sense to me, so I'll go for it, is because I've got all the formulae for these things, all I'm going to do, I've got a formula for the first finishing odd number, so I'm going to substitute Aleph0 into this, and I'm also going to substitute the number of consecutive increases being A into this. See what happens? So that's what I did. So first of all, because I've got formulae for the starting value of n, the finishing value of n, etc., I substituted, as I said, the value of A into these and got the values, what you can see there, formulae that you can see. Then I put the finishing odd number formula equal to LF0 and solve this for A, so to speak. So then I rearranged all of this and came up with the value of A in the blue box there. And that's with M involved as well for the nth time. So thus, the value of NCI for the nth time at which it goes to LF0 is greater than or equal to that value there. Now, if I want the first time, I just substitute M is 1 into this. Formula. Right, so obviously to check this, I've done the rearranging. Correctly, I can't really substitute infinity into this. I could sort of go backwards, substitute my answer into the previous thing and see what I got, but I thought, oh, that's quite hard. So I thought the simplest way of checking it is I won't substitute infinity into it. I'll just substitute a finishing value in that I found out before. So I knew that 4 consecutive increases started at n is 8 and finished at n is 40.5, as we found out before, and the finishing value was 161. So I thought, right, I'm going to substitute 161 into this with m is 1 and stuck it into my formula that I found out and basically got 4 increases. So I thought, oh, well, probably I've done the rearranging correct. Then I substituted those. All right, so I tried a consecutive and LF0 equaling 150 and came up with an A value of 3.936. So then 4 would be needed to get starting value to give that final value. Right, so I was sort of happy with that. Right, then the last reason is probably the main reason, really, as far as I'm concerned, the never-ending patterns involved, which I've sort of mentioned before, but I'll reiterate and maybe do another diagram as well. Right, so the never-ending patterns. So, as I said before, these NCI values take positive integers and these just carry on and carry on. So if it was 5 increases that occurred, the first n value was 2 to the power 4, 1 less than the number of increases, as you can see in the diagram there. Right, the first time that 4 consecutive increases occurs is directly between the first 2, 3 consecutive increases. The second time 4 consecutive increases occurs is between the third and fourth 3 increases. The next 4 were between the 5th and the 6th 3 increases, etc. This occurs for all the rest. If you look at the yellow 5, that occurs between the first 2 4s. The next 5 occurs between the third and the fourth 5s. This would just carry on forever, going up. And it's endless and suggests to me that obviously it would shoot off to infinity. Some values would eventually. Right, so this one, if you remember, just re-clarifying it, that was the first 4. That goes on to the second 3, goes on to the 5th 2, goes on to the 14th 1. Then the 5th one, the same thing would happen. The first 5 would go on to the second 4, would go on to the 5th 3, etc. So this pattern would go on forever. More importantly, perhaps, I might have mentioned before, if you look to the right of the diagram, the arrows, the black arrows, are sort of getting longer and longer because when you multiply by 3/2, go from one n value to the next n value, the bigger the numbers, the bigger the increase will be. And this will carry on forever. Right, so the summary of the investigation, which I'll read relatively slowly, but the cardinality or size of the set of natural numbers is Aleph naught or Aleph 0. The number of consecutive increases are positive integers. And so this set has also cardinality Aleph 0. The cardinality or size of the set of real numbers is 2 to the power Aleph 0 and is greater than the cardinality of the natural numbers. The cardinality or size of the power set of the natural numbers is also 2 to the power Aleph 0 and is greater than the cardinality of the natural numbers, or positive integers. Cantor proved that 2 to the power Aleph 0 is greater than Aleph 0. In the Collatz procedure, the first time that C consecutive increases occurs is that n is 2 to the power C minus 1, one less, and we got a starting odd number and finishing value and finishing odd number. And those particular things you can see there, the finishing value for n, sorry, and the finishing odd number. Right. An infinite number of increases would therefore potentially start at n equals 2 to the power Aleph 0 minus 1 and have a starting odd number of 2 to the power Aleph 0 plus 1 minus 1, which is 2 times 2 to the power Aleph 0 minus 1. It is impossible to have a starting odd number of that, as we know cardinality of the positive integers is Aleph 0, and Cantor proved that 2 to the power Aleph 0 is greater than Aleph 0, which in words is saying that the cardinality of the power set of the positive integers, or the cardinality of the set of real numbers, is greater than the set of positive integers. The cardinality of that is therefore follows that 2 times 2 to the power Aleph 0 minus 1 is greater than Aleph 0, as 2 times 2 to the power Aleph 0 minus 1 is at least equivalent to the infinity of the real numbers. Thus, there are not this amount of positive integers, and so a finishing value of Aleph 0, infinity of the positive integers, must occur at a value of NCI before Aleph 0. Right, when the finishing value of y is Aleph 0, then the number of consecutive increases is that, as we found out before. The starting value of n is that, and the starting odd number is that, to give a finishing odd number of Aleph 0. Right, I also found the jump height, as we found before, because of those limits, 2 being greater than 1 and 1.5 being greater than 1, that went to infinity. The ratio of the limit of the ratio of the finishing odd number to the starting odd number also went to infinity, and the other ratio went to infinity. Remember what Terence Tao said, the gap between the powers of 2 and the powers of 3 went to infinity. And if you multiply out the brackets in the blue box, 2 to the power of NCI times by 1.5 to the power NCI is really 3 to the power NCI minus 2 to the power NCI, if you multiply the brackets out, which is what Terence Tao was saying, the gap between the powers of 3 and the powers of 2. Right, now my overall conclusion. You can decide what I've been saying is total rubbish or you agree with me. Right, the vast majority of natural numbers will eventually go to 1. But due to the infinite pattern where the number of consecutive increases is increasing as the natural numbers increase, then there must eventually be some odd numbers that shoot off to infinity And this is all shown in the following diagram. Now, unfortunately, underneath my face, which apparently I can move, but it didn't move the last time I tried it. You can see that the last yellow box is LF0. Right, so what I've tried to put is show us the values of NCI are increasing diagonally. Now, if you look at the value of NCI being 3, I've put the n value is 2 squared, which is always 1 less, remember, and when I put 4n minus 1 into that, I get a starting value of 15, and that goes to 53. I also did this for value of NCI being 5, starting at 63 and going to 485. You can remember, I also did 23 consecutive increases, which would start at n equals 2 to the power 22, and got the starting value and finishing end value for that. So I put those on. Right, so what I'm saying then is that if the number of consecutive increases is LF0, then what is the starting Y value? Well, we're saying that because that's equivalent, as you can see in the yellow box, that's equivalent to the infinity of the real numbers, then that is greater than the infinity of the positive integers. So that is impossible, as it says in the yellow box on the left. Right, so then we sort of said that the infinity of the positive integers therefore must appear before that value. So that's what I've put in, and I've used the starting value of A for that. So then remember that I went for it and came up, solved N0 equaling the final odd number and came up with the answer there. Right, so that sort of covers everything that I've sort of mentioned so far, but probably those other 2 diagrams and the table that I found out before showed that the pattern carries on forever and ever. And that thus there will be some extremely large odd numbers that will shoot off to infinity. If this is the case, then the Collatz conjecture will be false. Right, so thank you very much for listening. Now I put part 2 there. Now what I've done also in part 2, I did the same for 5x plus 1, 7x plus 1, etc., and found the formulae for the number of consecutive increases for those. They're on similar lines to the 3x plus 1. So if you're interested in those, they will go to infinity again, maybe. If you're interested in those, then I can put the formulae for those online. I did those really quickly, so I'm not as convinced I'm correct for those as I am for this video. But in part 3, I looked at loops, and I thought I came up with a reason why there'll be no more loops in the 3x plus 1, but I'm not 100% sure about that. But I can mention it if you're interested. So as I said, thank you very much for listening. Now, if I've actually taught you before, or if you've been a colleague of mine, then I hope you're all well. And I don't know whether it's a reminder of you of my teaching style or whatever, but I really hope that you've enjoyed the video. And if you've enjoyed it and think it's useful, then please pass it on to other people. Thank you very much. I will try to stop the share and end the meeting. Thank you.